Okay, it's my pleasure and honor to introduce Shizong Zhang, someone I've had the pleasure of knowing now for quite a while. Shizong was educated at Tsinghua University for his undergraduate, and for his graduate work was Tony Leggett's student at the University of Illinois at Urbana. He then worked as a postdoc at Ohio State University, and in 2012, I think, went to HKU, where he is still today as a professor of physics, running a theoretical group in condensed matter and AMO physics. So today he's going to tell us about the effects of P-wave interactions on the statics and dynamics of ultra-cold Fermi gases. Please,
okay, well, okay, thank you, Joseph. Thank you very much, and thank you for all for coming. It's nice to see the faces. So just one correction. Actually, I'm still the associate professor, so not professor yet, because in Hong Kong this is something they take very seriously. So if I mistakenly write that, I think it will be counting as most likely probably some consequences. So I have to be addressed as doctor, not professor. So, but hopefully you will become, you will later become professor soon. Anyway, so thank you very much. So I want to kind of tell you some of the things I've been doing in the last few years. So mostly related to the P-wave Fermi gas, which in fact got started with Joseph's introduction, the experiment in 2015, 2016. So, so after that, I've been working on this for some time. So what I want to tell you today is essentially the main message is that as compared with the usual S-wave case where in cold atoms, the P-wave case has some kind of special features that one need to take into account when considering its properties. So especially the properties that I'm going to discuss are the energetic properties and also the dynamic properties of the P-wave Fermi gas. So the what is important in the P-wave case, as I will show later, is that the effective range has to be taken into account, and that has some consequences in both the energetics and also the dynamics. So, so maybe let me just. Oh, sorry. Okay. Okay. The first page is okay. So let me start with the S-wave case, which I think most of you know quite well. So if I have a two-component Fermi gas with only S-wave scattering at low energy and with a very short range potential, then we know that at low scattering energy, the effect of the interaction can be essentially captured by this low energy effective range expansion. So for the S-wave case, will be essentially K, which is a relative wave vector, times the cotangent of the phase shift. Then this has an expansion, which is given by the first term -1 over S, where S is going to be the scattering length. And then there is a second term, which is related to the effective range, which has a K-squared term there, energy-dependent term. So as you know, that usually for a really short range potential, this expansion is fastly convergent. So if I assume a real short range potential in this case, then the S, both S and RE are kind of on the face of at the first on the face of it would be irrelevant for describing the interaction at low energy. So then you can ask, for example, in the weak coupling limit, where the scattering length, in fact, is very small, or the parameter KFAS is very, very small, and the previous two, KFR0 much less than 1 and KFRE much less than 1, essentially the first one tell you that the system, in fact, is a dilute system. So the KFS much less than 1 give you the fact that it is a weakly interacting. And then you can calculate, for example, the ground state energy of the system. And the typical result that people usually quote is to the second order in KFS squared, that is so-called Li-Huan-Yang correction. So this gives you this 11 minus 2 log 2 factor here. But if you take into account the effective range, then there is an extra term, which is 1 over 5 pi times KFRE. So that also enters in the second order term in the energy expansion. So in fact, this people are still interested in calculating this. So the most recent paper is actually from 2020, where they have calculated, in fact, up to the 4th order in this expansion. So obviously, in high orders, the effective range would also come in. Now, another limiting cases where some calculation can be done is in the strong coupling limit. So in this case, again, we have KFR0, which is much less than 1, which again is a dilute system. But the KFS, this is going to be very, very large, so which means that it's going to be close to unitarity, where we have a scattering resonance. So in that case, actually, Schrenk and Pesik has done effective range, effective theory calculation, and for their effective field theory to be applicable, they require this KFRE to be essentially of order 1 or larger than 1 for their expansion to be correct. So, so in that case, as you can imagine, that there will be a parameter, which is usually called burst parameter of the energy per particle, where this 3 over 5 EF obviously is the energy per particle for free Fermi gas. And then this C KFRE, this function can be computed from the effective field theory. So they have obtained this curve, and actually this is not an exact calculation, because they have still they still have to estimate the errors they made, which is by the dashed line. But in any case, this is their result would become more and more exact when KFRE becomes very, very large. So, so this is, I think, the situation in the S-wave case in the energetics, where people have looked at how the effective range enters into this the kind of the classic problem of two-component Fermi gas with S-wave interaction. So then let me go to the dynamics. So for dynamics, in fact, in this case, I'll be only looking at one specific case, which is the bulk viscosity. The reason that bulk viscosity is interesting is that there is a very nice argument, very nice work back to 2007 by Dam Song and others afterwards, which show that, in fact, if you have a resonant interacting Fermi gas where the scattering length goes to infinity, then the bulk viscosity actually identically equal to 0 because of the scale invariance of the system. And the later people show, in fact, even the kind of frequency dependent bulk viscosity also goes to 0. So, for those of you who are not very familiar with bulk viscosity, I'll come back to that later. But here I simply want to set up kind of the reference point. So now, if you actually add into the consideration not only the scattering length, but also the effective range. So remember that even if the scattering length goes to infinity, so you lose one of the length scales in the problem. But now if you take into account the effective range, then you add into another length scale. So that length scale would also break the scale invariance of the system. So in that case, you would expect to have a non-zero bulk viscosity. So the question, of course, is to calculate what is the dependence on the effective range. And in particular, you would like to know whether the effective range well, the correction from the effective range is relevant or not irrelevant. Here, what I'm thinking is, in fact, as you know, that if you do a S-wave kind of a simple RG analysis on the different rho by scattering length and also the effective range, you show that in the S-wave case, the effective range is an irrelevant perturbation of that term, but the scattering length is the relevant one. But this seems to indicate, for example, that even in dynamics, that the effective range would be kind of an irrelevant perturbation. But since dynamical quantities are quite kind of different from the static property like energetic, so that requires a kind of a separate calculation to show explicitly. And also, so this expression is for the zero frequency part at resonance, where you see that the effective range dependence is Re squared, and Z here is essentially the Viscosity. Where this is the calculation by Jeff Markey, and then this lambda T is the sum of W wavelengths. So I'll come back to this result later. And you can also calculate at high frequency what this result would be. And here, so for example, when omega goes to infinity, and also for the case where when the effective range goes to 0, so you get to the standard result that people have already derived, for example, in Taylor and Renderius work in 2010. But you can also ask, when the scattering length goes to infinity, which means that scattering length drops out, and you can ask what is the effective range dependence there again. So here is give you the square root of omega dependence in contradiction to the 1 over omega 3 over 2 dependence. So which means that there is a divergence of Barkov viscosity at high frequency, which is like a square root of omega with a coefficient which is given by Re squared, the effective range squared. The CIS is the so-called contact of, but at resonance, it's simply a number that you can regard as a constant. So from these two expressions, obviously, the high frequency dependence, frequency dependence are quite different, whether you take into account the effective range or not. So, so there also a calculation for if you have a finite 1 over AS, 1 over AS, which is where you deviate away from the resonance, then that again the scale invariance is also broken. In that case, there are also calculations done earlier by Nishida and Tillman and also Johannes Hoffman. So there are some subtleties there, which I'll mention later in relation to use the kinetic theory and also the Kubo formula in calculating this quantity.
Shizong, maybe you could just say, for people who haven't thought about this before, what you mean by what scale invariance you're talking about, and what that means for what is a scale invariant system in this context.
Okay, so actually, I think later there will probably a slide which will explain this. A scale invariant system in the unitary Fermi gas is the interaction parameter. If you, let's say, if you forget about the effective range, so you only have scattering length. So if the scattering length goes to infinity, then the only scale you have is the interparticle spacing, or which is equivalent to the KF, inverse KF. So in that case, all the thermodynamic properties obviously will be only a function of like the energy would be simply proportional to the EF, but there are most kind of severe constraints because of the lack of scattering length as a parameter in the theory, and that relates to if you rescale the coordinate of the system. and because of the zero range model that one uses, and the fact that the scattering length goes to infinity, you will show that in fact the system is invariant under a scale transformation, which is change the distance by a scale, let's say lambda. So I'll come back to that later, and so that gives you for example, the vanishing of the scale of the bulk viscosity. So here so in the first two slides, I simply want to say that even in the S-wave case, you still see the kind of the rule of effective range plays, especially in dynamic quantities. For example, in the bulk viscosity, the frequency-dependent bulk viscosity, it actually changes the high frequency tails that you can hopefully measure in the experiment. Okay, so now most I want to say, in fact, in this talk, it will be P-wave. So this will be the discussion so far will set up some reference points we come back to compare later. So I'll be quick on this part. So so for the P-wave scattering, of course, we have as you know, this effective potential with the short range potential by add into this centrifugal barrier. So you have this typical form here. There is the height of the barrier. There is distance away from the origin where you have this maximum barrier height. So there are a lot of experiments on this. And I think the most recent, I think Joseph had a characterization of this scattering of the P-wave potassium gas. So in that case, all these parameters, in fact, in the long range part are known for potassium and lithium. So I'm not going to kind of say the numbers here. But what happens is that I put all this here just to say that in the calculation that I'm going to do, I'm going to assume that again that the low energy scattering, it depends only on a few parameters, even for the P-wave case, and I'm going to neglect the van der Waals interaction. The reason for that is that for van der Waals interactions, the P-wave scattering, this for P-wave scattering is not sufficiently short range to some extent. So this there'll be extra terms in this expansion, but close to resonance. In any case, these extra terms are not going to be very important. So so I will be continue to assume that the effective range is going to be expansion is going to be valid. And in the P-wave case, the expansion takes the same form, except that you have k to the 3 times the quotation of the phase shift. And then this expansion gives you the first term 1 over v, which is the scattering volume, and minus r1 times k squared. So, so the questions that I want to say or investigate is how this effect effect of the P-wave interactions, the scattering volume, and in particular, how the effective range will comes into the energetics and also the transport properties of the P-wave Fermi gas. Before I get into the discussion, so one kind of final slides on these simple two-body problems. So in the case of the S-wave, you have this radial potential, which is kind of asymptotically goes to 0 from below. So when you have a bound state, EB, the bound state wave function is given by this standard form, the radial wave function 1 over r times the exponential times 1 over minus 1 over as, where as give you essentially the size of the bound state. And the bound state energy is given by this h bar squared over 2m as squared. Now this bound state only exists when the scattering length is larger than 0. So in contradiction, in the P-wave case, you actually have, because of the existence of this centrifugal barrier, and I think if you remember, the barrier height is quite large. In fact, for potassium, I think, is 5 megahertz. So usually the energy we are considering for the dimers is very, very small. This centrifugal barrier. So you can also have a bound state. The bound state can below the threshold, below the zero energy. So in that case, you would have a true bound state. And in that case, the scattering volume is going to be larger than 0. And the bound state energy is given by this expression, h bar squared over 2m v times r1. So I forgot to mention before that v, because it's scattering volume, it has dimension of length to the third power. And r1 is an effective range. In Pwl case, it's 1. So just come before this k squared. So this entire thing has to have 1 over volume. So so R1 then in that case has dimension of wave vector instead of length. So I'm using not the same notation as we did before, just one. So in this case, so h bar squared over 2m v times R1 is v times R1 essentially give you the length square. So this is the energy scale. So the other thing that is different from the S-wave case is that the normalization for the P-wave wave function, in fact, depends on the effective range as 1 over square root of 1 over 2R1 here. So then we have the true bound state has energy, which is kappa squared over 2m. And again, that you have this form wave function here. So, so these are just the 2 body bound state, and you see there, at least for example, you see in the case of the P wave, you do need a finite effective range to give you a finite bound state energy in this case, because if R1 is not in the effective range expansion, then this bound state energy would be essentially goes to 0. So now let me, so what I will do now is I will first discuss in the Pwl case, what is the normal state properties in the Pwl gas, and then I will discuss the viscosity of the Pwl gas. So this is being by request of from Joseph. So just very quickly was to say what I'm doing. As you know that for the normal Fermi systems, so kind of a semi-phenomenological theory of normal Fermi system is essentially given by Landau's Fermi liquid theory. So in that theory, what you do is that you essentially look at this momentum distribution. I'll draw this here in 1 dimensions, and so you have let's say ideal Fermi gas. In the case of ideal Fermi gas, you have this at t equal to 0. You have this distribution function up to kf here, and it's a step function. But when you take into account there is interaction between the particles, then because of the Fermi exclusion principle, then you will imagine that below the Fermi C or deep below the Fermi C, nothing really changes, but the distribution would change close to the Fermi C. And I'm cheating a little bit because now one is in fact really talking about the quasi-particles. But in any case, you have if you can define the NK from the non-interacting case, and then essentially use adiabatic continuation to label the interacting system by the same delta NK. So when you take into account the interactions, then this momentum distribution would essentially change close to the Fermi surface, and then you kind of describe the system by a set of numbers, this delta NK. So then what Landau did, as he always do, is to expand to second order in small parameters. So here you will have essentially the energy minus mu n, or the free energy of the system, is expanded into second order. So there will be a first order, which is this EP sigma minus mu. This is considering 2-component Fermi gas, and multiplied by this change of the occupation number. And then there is a second order term, which is expand to the second order of energy with respect to the quasi-particle distribution here. So basically, these are the change of the occupation number as compared with the non-interacting one. So this will be second order. Now, of course, the genius of Landau is that you need to realize that you actually have to expand to second orders, because these two terms are in fact of the same order because of the minus mu here. And the delta square E here, you don't have to keep mu A in here, because this only goes to the first order term. So this essentially only picks up the correction or the derivative from energy. So in any case, so this is going to be a kind of the expansion that you have for the energy of the interacting system. So from here, you can define a few quantities. First, you can define the Fermi velocity at around the Fermi surface, and kind of defining character of normal Fermi liquid theory is that even though the jump of the nk from the non-interacting case, which is going to be from 1 to 0, for the interacting case, even though this jump is going to get diminished, it never goes to 0. And and in particular, or in addition, if the system has isotropic interactions, then the Fermi wave vector also is going to stay the same, is so-called Latinger theorem. So which means that Kf or Pf stays the same as the non-interacting system. So in that case, the dispersion obviously will change. So you can define the Fermi velocity by simply taking the derivative of Ep with respect to the magnitude of P. So, and then the effective mass is simply given by the Fermi momentum divided by Vf. So these are the kind of a few parameters which describe essentially the quasi-particle dispersion close to the Fermi surface. And then you have this interaction between the quasi-particles, and so these are defined so-called the Fermi, the Landau functions. So they are the second order derivative of E with respect to the delta NP and NP sigma, NP prime sigma prime. So because we are only considering the case where very close to the Fermi surface, so the Fermi Landau Fermi functions, Landau functions actually is defined by setting the P and P prime equals to PF. So then the only dependence apart from the spin dependence is the dependence between the angle between P and P prime. So this is the cosine theta here. And so this is Fs cosine theta. This is the symmetric part. And then there's a part that depends on the spin, sigma prime. So this will be the antisymmetric part. And both of them depends on cosine theta. In fact, as I will show later, in our case, because we are considering a spinless P-wave Fermi gas, so our job is actually quite simple because we don't have the spin. So this second term essentially is gone. We only have one Landau functions to consider. So the dimension is Landau parameters because this guy has dimension of energy. F has dimension of energy. So to make them dimensionless, one essentially multiplied by the density of state at the Fermi surface, or actually half of the density of state at the Fermi surface here, because it just corresponds to the one component. So the only message you want to take from this slide is that this Fs and Fa essentially give you the interaction between the quasi-particles, characterized interactions, and it is a dimensionless number. Okay, so just to give you one example, so in the case of two-component Fermi gas, so this calculation has already been done in the very early in the 58. So you can calculate all these properties of the system. For example, let's say this gamma p is the lifetime of the quasi-particles, which has this p minus kf squared dependence. And then you can calculate the chemical potential, the effective mass, and the total energy of the system. So here I'm quoting something slightly different. But what is important here is this quasi-particle residue Z. In this case, you can calculate, which is going to give you essentially 1 minus this number here. So this KFS in the weak coupling limit, sorry, this should be AS here, the scattering length, KFS. So if KFS is very small, this actually provides you with a very small correction to the Z, which is the jump around the Fermi surface here. That's the number here. So this tells you, in fact, that at least in this model calculation, that you have indeed explicit calculation which shows you that the Fermi liquid theory, the concept of Fermi liquid theory is valid, and it does produce for you all the kind of the correct characterization which is given by Landau Fermi liquid theory. Now, one thing that I should say straightforward is that in the Pwl case, what I will do is I will try to essentially repeat this calculation for the Pwl case, but it turns out that the quasi-particle residue in the Pwl case, at least to the order that we are calculating, actually cannot be computed. It is not defined in that calculation. So that's some problems likely to involve in three-body and other high pressure wave scattering. So which we are afraid to do. So we just so far left it there. So now maybe since I'm going to do the Pwl case, I would like to mention a bit why it is different for the S-wave and the Pwl case. So if one take a look at the S-wave case, so the S-wave scattering phase amplitude is given by this FSK is going to be have 1 over minus AS inverse minus IK. And so people know this. And if I have the kind of the contact interaction before essentially this parameter G here, the coupling constant here, I know how to relate that G to AS by doing this essentially a two-body calculation. Now, what is crucial here is that for the S-wave case, since we are so far, at least here, only interested in the dependence on scattering length, not on effective range yet. So, and the effective range is going to be a quantity, essentially is the energy independent part or independent part of the scattering. So what that means is that this calculation I'm doing for the two-body calculation, which relates this Bayer coupling constant to S. So what I'm doing is going to do a on-shell scattering, because that's how it is related to the scattering amplitude, which has this AS dependence. So I'm going to do a on-shell scattering with this Bayer coupling constant G, and then I'm going to match it up with the scattering amplitude. Now, because in this case, we are only going to be we only need to worry about the on-shell scattering amplitude for fixing the relation between G and AS. But in the many-body calculations, as you know, you have to sometimes to calculate off-shell scattering amplitude or vertex functions. And what happens is that in the S-wave case, actually it's actually quite I think fortunate, is that when you have these renormalization relations, and to make sure that the on-shell properties are finite, and then automatically the off-shell scattering amplitude are finite as well. Now in the Pwl case, it's slightly different.
Shizong, could you just quickly say what you mean by on-shell and off-shell?
I think the next slides would come. Okay, so in the Pwl case, the renormalization actually needs to be done up to the effective range level. Now, this effective range has a chi-squared dependence, so which means it is the energy-dependent scattering that one has to consider. So, so unfortunately, it turns out in the Pwl case, you can manage to, for sure, do a on-shell calculation to make sure that you match the bare the bare potential with the scattering parameter here, the scattering volume V and the effective range R1. But when you want to do off-shell calculation for vertex function and things like that, then you encounter infinity. So in the S-wave case, you don't, but in the P-wave case, you do. So this, in fact, is one of the reasons why the causal particle residue in our calculation is simply not defined. So I'll just make one comment, and then I'll come to the off-shell scattering shortly. So for the P-wave case, now just to note here that in the unitary limit corresponds to when this, essentially when these two terms goes away, which means the V goes to infinity and the effective range R1 goes to 0. So you're left with only the term which is essentially fixed by the unitarity condition ik to the third power. So just to make the comment, Joseph's comment, what is off-shell scattering? So actually, we'll make simpler ones to look at the half off-shell scattering. So which means that it is the FP KK prime. So K and K prime, let's say K is the relative wave vector of the incoming particles, and K prime is the relative momentum of the outgoing two particles. So in elastic scattering, obviously K and K prime, the magnitude has to be the same because the energy has to be conserved. They can have different directions, but the magnitude has to be the same. So, but in this case, this is so-called half off shell because the energy is on shell, but this K is not on shell. So this relation is basically this relation here, FP K prime K. So it will be equal to J1 is the first order Bessel functions, VR is the short range potential, real potential, and phi P, this is the actual wave function, P wave function of the system. So in this case, if you put K equals to K prime, then this FPK essentially is going to give you the scattering amplitude, where you can do the effective range expansion to give you the 1 over V and an R1 term. But more generally, you have this half of shell ones. And in many-body calculation, you also not only have KK prime dependence, you also have omega dependence there. So that will be the kind of the many-body where the energy is also not on shell. So this equation essentially come from the kind of the Lippmann-Schringer type of equation. So if I now want to analyze this structure of FPKK prime when both K and K prime are small, so that's where we are going to look at its at low energy scattering. So then what you can do is essentially to expand J1, which is Bessel functions. So the first term is K prime R, and then you have 1 minus this K prime squared, R squared divided by 8. And then you can also expand the actual P wave scattering wave function, phi PKR, and then there will be a factor of K in front, and this simply because it's a P wave scattering. And then you have the first order term and the second order term here. So if you substitute this expression into here, into the integral, and then you will find that FP K prime K in fact equals to KK prime, which is the kind of the form factor you want. And then there is a first order term which depends on does not depend on K, which is essentially the 0th order term multiplied by the potential multiplied by R integration. And then you have 2 terms here which depends on K and K prime, both to K squared term. Now, just imagine that if you have K equals to K prime, these 2 terms can be combined together. So essentially, you just k squared times these two integrals add together, and that will give you essentially the f scattering amplitude, and that you can compare with the scattering, the effective range expansion. That will give you, for example, the first term would likely to correspond to 1 over v, and these two terms combined together would give you the energy dependent part of the scattering parameter. But now if you have k is not equal to k prime, you have a problem, because here these two terms are independent. So which means that to characterize this, at least even for this half of shell scattering with energy dependence, then you need one more extra parameters to do that. Not only the scattering volume or effective range, but something more. In other words, you need to know more about the potential in order to know this parameter. So so in the many body calculation, in fact, you are going to have not only this kk prime, as I said, you also have the omega dependence. So in that case, your expansion is going to be slightly more complicated. So you need actually more parameters. So you just, so fortunately in the S-wave case, all these complications is gone, but in the P-wave case, one has to kind of work on it. Okay, so so in any case, so you can just sit down or your student can sit down and try to do the calculations. So you can again find all the ground state energies and effective mass. So which I'm not going to go through, except to say that one thing that is important is that because of for the effective mass case, because of the scattering is momentum dependent. So in the S-wave case, the effective mass only receive contribution from the S-wave scattering to second order. But in the P-wave case, it receives a contribution from the first order term. So in that case, depends on the sign of V. The effective mass can be either larger or smaller than the bare mass. Okay, and you can also calculate the. This is essentially the Landau F function. You can also calculate, again, here there's one thing which is slightly different from the S-wave case. That's why I want to show you is that if you look at the Landau parameters again, then the first one is the zeroth order, the angular momentum is essentially the expansion, this f cosine chi, which is the angle between the two, and then you do a Lorentz expansion, then the coefficient is the Landau parameters there, and f0 in fact is proportional to the first order in kf third v, and f1 is in fact to first order in v is exactly the opposite, or the opposite minus of f0. And in the S-wave case, in fact, f0 turns out to be first order in the scattering length, and then all the high order terms f1, f2, and they are all going to be second order in A. So in this case, just because of, again, this is related to in the P-wave case, you have this angle dependent scattering, the k prime, k dot k prime term. So that gives you this these two terms here. So this is kind of nice, and you can make sure that that some of the exact Fermi liquid relations also holds. For example, the effective mass relations and also the sound velocity of the system, and all work out from the calculation, satisfy those conditions. So maybe just one, yeah.
I'm sorry to interrupt. We're about 5 minutes to the hour. So
okay.
What I suggest is maybe you try to wrap up in the next 5 minutes or so, and then we could pause for questions. And then I think you have a little more to say than you can say in 5 minutes. So we could have a kind of coda that involves people who are really working with P waves, and I think a lot of my group would stay. But I think
Okay.
maybe we kind of do it in 2 parts.
Okay, sure. Okay, so chatty. So let me just skip this part. There's one consequences of the fact that F0 and F1 both to first order in V. So let me skip that. I do want to go to the part of the bulk viscosity. So just to give you the punchlines. So so this is the part corresponds to the scaling and invariance of the system. But let me go to the final slides here. Yeah. So so the viscosity, the bulk viscosity of the system in the S wave case and in the P wave case, and at least people all know, as I said before, that if you have effect range dependence, then you would expect that the bulk viscosity would essentially take a finite value at even at resonance. So here I'm kind of giving you the high frequency limit for both the S wave case and the P wave case, and the zero frequency limit. So I would just want to highlight some differences. So in the S wave case, you see that as we showed in the first two slides, you have because of the existence of the effect range, you have a square root of omega dependence with RE squared term. But if you see this expression, so these are the leading terms of the high frequency limit. If you take the effect range goes to 0, then certainly that all this expression actually just vanishes. So RE here goes to 0. There is one RE here, but they cancel out. So all these terms, the leading divergent terms in high frequency goes to 0. On the other hand, in the P wave case, as I said before, the scaling, the effect range goes to 0 limit. It corresponds to when you go into the unitary limit. In this case, the effect range actually is going to appear in the denominator, which means that in this case, you can't really set effect range goes to 0 in your calculation. Otherwise, your result would simply blows up. So in other words, the effect of the effect range in bulk viscosity in the P wave case is a highly non-perturbative result, not like in the S wave case where you can have essentially a perturbative result. The same result also holds for the zero frequency limit, where in the S wave case it's proportional to the effect range squared, but in the P wave case it's proportional to 1 over R1 squared. So they have even let's say at resonance, where you simply set AS goes to infinity and V goes to infinity here, you see that the quite different dependencies for the effective for the bulk viscosity in the S wave case and in the P wave case. One is proportional to RE squared, and one is proportional to 1 over R1, which is effective. So again, so this is non-perturbative. Maybe just if I have a last few two sentences, is that so before here I'm giving you essentially the kind of the high frequency, high temperature result. So you would expect that. So this is a calculation using Kubo formula. You would expect that at high temperature, you would expect the Boltzmann equation simply to apply, and you should be able to see all this in the Boltzmann calculation. So that's what we did. We also tried to use the Boltzmann calculation, but in fact, we have to take into account the self-energy of the quasi-particles, put it back in the Boltzmann calculation. And one thing that we find, which we don't know exactly what happened even now, is that in the S wave case, in the P wave case, we can essentially reproduce the terms, dependent terms, how the effective effective range enters into the bulk viscosity. However, in the X-wave case, we find that the calculation based on the kinetic theory or Landau-Boltzmann equations and the QOAMO formula in terms of the the correlation between the stress tensor give you quite different results. So in the case of the Boltzmann calculation, give you essentially RE to the fourth power instead of RE to the second power. So that part we still don't understand why. And if some of you have experience with the Boltzmann calculation, would be happy to know. In fact, in order to get this result, we essentially put into the calculation by fiat the imaginary part of the self-energy in the kinetic equation. In any case, but then seems to give us the correct result. So there is still a discrepancy between the Boltzmann calculation and the QOAMO formula calculation, and that difference also appears when you are considering when, let's say you don't have any effective range, but you simply have a breaking of scaling variance by a finite scattering length. So in the Boltzmann calculation, you get this 1 over AS squared, but in the QOAMO calculation, you get this log AS divided by AS squared. Again, I think this part is still not very well understood. So with the effect range, I said that the dependence of the power of effect range is different, and the first term here is again the same as the previous calculation. So I think, sorry, that I think I should probably stop here and if there's any questions.
Great, thank you.
No, I think it's a really horrible.
Okay, so.
Oh no, I didn't mention it. I didn't manage to get this stuff. Yeah.
Yeah, we can pause for questions now and then continue to see the things we didn't give you time for. Let me especially encourage any graduate students to either type something in the chat or unmute themselves and ask a question.
Yes, I had a question.
Yes.
Is the high frequency divergence in the bulk viscosity for the S-wave gas, is that real? Is that physical? Would that be observable in some way?
I think in fact I think it would be real. So I think when we say high frequency, of course we are considering high frequency, which is much smaller than the frequency set by the two-body scales. So in particular, if I go back to, I don't know whether, I think it's easier to go. So for example, we always will require that this high frequency which be much smaller than 1 over RE squared. So that's kind of the low bar for. So it has to be much smaller than this. So I think then it just depends on whether the experiment has a window where this can be seen. So for example, I think we estimated in the calculation with Jeff, if you take the, so for example, potassium 40, I think where KFRE is still going to be, I think KF times, or in this case, KF divided by R1 is still going to be 25 or around 25, 24, right? The number. But no, sorry, 0.4, yeah. Yeah, 4%.
0.04 or something like that, 4%.
Yes, yeah, 4%. So that means if you just take that as an estimation, that means if you go to the high frequency, which is the high frequency much smaller than a few hundred Fermi energy, which is 20 kilohertz times a few hundred, I think there is a very large window where this can be seen. Yeah, but I think the problem is is that whether in that window there are other effects which comes here. So these are only, for example, take into account the effect range part, but in when you go to that high energy, then I think there are other terms which might come also.
Other questions? I have questions, but they're kind of specialized questions. They're not general questions. Okay. All right, if there are no further questions, then I think maybe you can show us some of the stuff that you skipped to get to this point, and then those who are have other time commitments, you know, we won't shame you if you slink out of the room. So feel free to do that, or stay and listen to a little more about this topic. So, yeah, please.
Okay, so okay, sorry that I kind of forced upon you. Let me just be quick on this.
No, that's fine. I forced upon you explaining Fermi liquid theory, so that's not fair. Yeah.
Okay, so maybe let me just go to the bulk viscosity, since this seems to be the more interesting part. So again, this is at the request of Joseph. So if again I take longer time, then that's his fault. Okay, so what is the bulk viscosity? So if you go back to the fluid mechanics, the kind of one of the Euler equations has this form. Partial T rho times Vi. I is the Cartesian directions. Rho is the mass density in this case. So it will be equal to this partial pi ik partial xk. So this is pi is essentially the momentum energy momentum tensor. So this is essentially express the fact that the momentum conservation in the system. So but when there is kind of dissipations in the system, so you can kind of add into this energy momentum tensor a part corresponds to essentially the decay of the momentum in the system. A term which is given by sigma prime ik. So the first two terms here, in fact, just is given by the standard expression. P is the pressure, and then rho times Vi Vk. So this extra term sigma prime here is going to describe the dissipation in the system. And then according to the standard arguments that you are going to expand to essentially to the first order in the gradient of the velocities. So you're not going to consider high order gradients in velocity. So those are smooth kind of smooth flows. And then this will, the sigmas by symmetry analysis will be only having these two type of terms. So first, it will only depends on this partial Vi, partial xk, the combination of these terms. And then because of the rigid rotation does not contribute to dissipation. So you are only going to have essentially the kind of the symmetric combinations of those partial Vi, partial xk. So in that case, you can write this generic term in two terms. One is the stressless one with a coefficient which is called eta. So that will be correspond to the shear viscosity, and then there will be this all the trace parts. So this one, this will be corresponds to the bulk viscosity. So for example, in the case of a typical experiment, if you have a so-called breezy mode or monopole oscillations, the velocity field here actually is proportional to essentially lambda t times x and y and z. So which means that the velocity is going to be become faster and faster as you go away from the center of the cloud. So because this V has this form, then the first term here essentially goes to 0. You only have this second order term which is operative in damping the system. So for the breezy mode or for the monopole oscillations, essentially it's the bulk viscosity which do the damping. And how it dampens the system, you can essentially calculate how the energy are got lost in kinetic energy are got lost. So if you have kind of small displacement, then you can actually show that this kinetic energy will damp exponentially as a function of time with a proportional constant, which is given by this averaged over bulk viscosity. So in any case, so this is maybe kind of one way that you can measure in the bulk viscosity in the system. So just look at how the amplitude of the oscillation damps as a function of time. So then, I guess, so then why, I think Joseph asked before why this scale invariance is important. So in the S-wave case, you can see that if indeed the scattering length goes to infinity, then you have something quite nice. So one way to kind of see that is to look at the many-body wave functions that you have. So this phi defines the many-body wave function of the system. Xi describes the spin up, and Yj describes the spin down particles. So for the S-wave scattering, if you don't have effective range corrections, then if you only have the 1 over S term, which is the scattering length, then one way of formulating the many-body problem is to say that if I take in this many-body wave function any particle with spin up and then spin down, and then I move them to be close to each other, and then that many-body wave function must have this asymptotic form given by 1 over the distance between these two particles minus 1 over S times some remaining part which will be regular as a function of Xi minus Yj. So this is essentially just reformulating the problem that you have the two particles scattering with the S-wave scattering length, 1 over S. So if you go back to the two-body case, in fact, you can show that the two-body wave function in the region outside of the potential would have this particular form for the two-particle case. So then if you perform a scale transformation, namely that even for the time-dependent ones, you don't have to be time-independent. So then you simply change the distance by a factor of lambda t for both x and y, and you put it back here. Then what happened is that this boundary condition, usually referred to as beta Pwl boundary condition. Then if you substitute this back into this expression here, you will have this phi, which is now in terms of this rescale quantity. So you put it back here, you have an extra factor of lambda divided by xi minus yj. Again, this term does keep the same, 1 over as. But then I can simply kind of divide this lambda and put it into this this factor here, this a become a prime, redefine it to be, because this is kind of the normal part or regular part, doesn't really matter. So the only change is that you are going to start, once you do this scale transformation, you are going to start with the system scattering with scattering length S. But now once after the scale transformation, you have a system kind of with a scattering length 1 over lambda S. So just change this to the same, to lambda S. So you changed the problem to a scattering with a different scattering length. But what is nice in when S goes to infinity is that this term just goes away. So no matter how you do it, you're only left with the first term, and that is invariant under this transformation. So namely, no matter what you do, you are always going to be at resonance, and the property of the system is always going to be given by this unitary condition.
This is actually really neat to see, because we've been actually Tillman Ince had this suggestion of the way to think about wiggling the scattering length around infinity, that we were essentially it's like measuring a conductivity, except instead of wiggling the force, you're wiggling scale. And so like a perturbation of the scattering length is, for the arguments you've given here, actually, because I don't think he had this, at least at the time, maybe this was almost a year ago when he said this, but if we take a small oscillation of the scattering length around unitarity, it's effectively like we took space and wiggled the scale of space. So if you, so you're, in a sense, you're driving a scaling transformation with the scaling, but because we're not magicians, we can't actually increase and decrease space-time or just space around our, our atoms, but we can oscillate the scattering length. And, for this argument that the last two lines here, it kind of says that when you wiggle the scattering length around unitarity, then
you're wiggling this, you are doing the scales.
It's as if you took space and drove a scale transformation, oscillated. And so then the response, which is bulk viscosity, is naturally probed by an oscillation of the scattering length around an oscillation of the scattering length. Yeah, so it's just a nice way of seeing that those two things are equivalent if this ansatz is correct.
Yeah, I think Nishida has a paper on this, I think some time ago.
Okay, yeah, okay.
Yeah, actually, Jeff and I and Faye, I think we'll come to that later. I think something which close to this, because this kind of scale transformation is time dependent, so it has consequences for dynamics as well. Especially, for example, as you say, if you design a time dependence for AS, and then to see how the system respond, and it's quite different. It depends on the time dependence of AS. Okay. So then this standard argument by Felix Warner and Ivan Castan. So if you take this, actually this probably known quite some time ago, before I think in their paper they will cite some earlier papers related to this. So if you have this time-dependent Schrödinger equation and has this in a harmonic trap, and this equation, in fact, is exactly satisfied. So here we are doing this scale transformation, and so if you take an ansatz of the wave function time dependence, but the time dependence only through this kind of the rescale of the system coordinates. The x is the kind of collection of coordinates that you have. X and Y before, and then you have this exponential factor here. You have this theta t, and then you have this overall factor, which is give you n is the number of particles. This basically give you the normalizations because of the change in the x, the distance. And this term, basically, you can also obtain from there. Then the question is to the theta t also you can write it down. But if you put this back into this expression here, then this will be an exact solution of this equation, provided that this equation here, the lambda has this particular time dependence. And remember, this phi here is not a free particle wave function. And in fact, it is the wave function which satisfies the kind of the boundary condition which I said before. So it is the wave function describing at unitarity, and satisfy that condition. So in that case, the Hamiltonian here, as you see, it only have the kinetic energy, because it's kind of the two ways of formulating the problem. If you formulated the problem in terms of specifying what is the boundary condition that you want the wave function to have, then the Hamiltonian is very simple. It's simply the kinetic energy, and then you just have to work with a very awkward boundary condition for wave functions. Otherwise, you can simply write down the interactions between the particles. But then in that case, your wave function does not have, you don't have to kind of specify that boundary conditions. But in this case, anyway, so so this phi has the boundary conditions before, and as we show that once you rescale it, this phi at resonance still going to obey the same boundary conditions, which means it's still a solution of this time-dependent Schrödinger equation. So this this expression give you the kind of the time dependence you would like to have for the lambda t. So if you kind of do a small expansion of lambda t around 1 plus epsilon t, and you put it back into here, you will see that this time dependence of the small oscillation part is exactly at 2 omega, where omega is essentially this, well, actually, yeah, actually here I have omega depends on time, but so that will, but here actually when I'm doing this, omega are set to be a constant, which is the trapping frequency here. So in that case, you can solve for it, and that give you the frequency of the small oscillation to be exactly twice of the trapping frequency, as you know. So the upshot of this argument is essentially that let's say if you imagine to prepare your system at unitarity, and then you kind of excite a small oscillation in the harmonic trap, then because at any instant that wave function is going to be, well, the monopole oscillation, as I said before, is essentially an oscillation kind of stretching over the coordinate. So in that case, this wave function always remains to be against, not against it, but always satisfy the time-dependent Schrödinger equation. So which means there is no dissipation at all in the system. And that, as I said, that dissipation is only refers to the bulk viscosity, because that's the kind of the breathing mode of the system. And in fact, you can calculate this lambda, and then you can show, in fact, the x dependence give you indeed that the velocity field, in fact, is going to be given by lambda dot over lambda. I don't know whether I have it. No, I don't have it. So the velocity field is lambda dot over lambda. So that v, and times x and y and z. So that's the velocity field. So this is a consequence of the fact that you are at unitarity, where you don't have this length scale. So in some way that you have any of these monopole oscillations always kind of ride on the time-dependent Schrödinger equation. So you always remain in the eigenstate, not in the eigenstate, in the time of evolved eigenstate. So that gives you that zero bulk viscosity for any frequency. So I don't know how much you want me to get into details of. Sorry for the. I can talk for a long time. I can talk.
Yeah, well, I'm also aware that it's half an hour past midnight your time, but
no, it's okay. You know, I just feel that it's.
Tell us 10 minutes more. I mean, I want to hear about how that's different for the p-waves.
Okay, so again, this the Cooper formula calculation is essentially straightforward. We copy it from Lattinger's 64 work. So he does in the appendix, he does derive all this formula for you. So I don't have too much things to do there. So this is essentially defined as the retarded correlation function for the pi and pi. So pi is the energy stress tensor. So yeah, for the unitary Fermi gas, is something quite nice, because there is this scale analysis where you can actually write down the operator form for this energy momentum tensor, and it turns out to be having this form where HL is so I'm formulating it in term for both S and P wave case. So L equal to 0 would be for the S wave, L equals to 1 would be for the P wave case. So in this case, you have this essentially the Hamiltonian operator for the S and P wave case, and this C and this C here is going to be the so-called contact parameter. So in the S-wave case now, I'm going to also include the effective range in this calculation.
Okay, and just to relate this to what we do in the lab, we jump the scattering length, let's say of S waves, and when you change the scattering length, it's like at time equals 0, we make a perturbation, and then we're measuring the response of pi at time equals t by looking at the contact at some later time.
Mm-hmm. Yeah.
So we're measuring this time correlator
For C.
By measuring the contact after a change in the scattering length. Yeah.
Yeah. Yeah. So then once you have this operator form for pi, then the rest of the things you just simply put it back, and then now there's a subtlety about this H because there's a Hamiltonian operator. In thermal equilibrium, the Hamiltonian operator has, if you take take a commutator with any operators, it will give you 0 because it's in thermal equilibrium. So that that creates some problems. But for us, in fact, this is not important for the calculation we are going to do. So we can simply neglect this Hamiltonian part because it gives you 0 expectation value in this commutator. And then you're only left with this correlation between the contacts. So this is already, people know this from Thielmann's work and Nishida and other people, Hoffman. So the rest of the things is, I don't think I should go through it, but essentially just to calculate these correlation functions with, we know the operator form for C relates to the scattering volume or scattering length. We also know the operator form for relates to the effective range in both S and Pwl case. So then you just have these terms to evaluate. So that's what we did. You take this 2-channel model, I think we know in the S and Pwl case, and you do the standard calculation. So basically, these are the form for the S-wave and Pwl case for the operator form for the contact. And then you do the calculation. In fact, it turns out the calculation can be quite streamlined. So you, for example, you have this expression here, and I don't think, again, I think you just have to sit down and then write it out. And in high temperature limits, we are only going to consider essentially the diagrams corresponds to, or the physical process corresponds to 2 particle comes in, scattering and form a molecule, and this molecule dissociate again, and then form a molecule again. So this repeated process. So in fact, if you can show that from the expression that this bulk viscosity is in fact an even function of frequency, which means that the magnitude of the energy absorption or energy release because of the, if you drive the system, you can either feed the energy into the system or extract energy out of the system. So omega and minus omega at t equal to 0 simply corresponds to those parts. And at finite temperature, it's slightly different because of the thermal factors. But you have this relation where it is an even function. And you can also derive the sum rules for this also. This is essentially what Ed has done before, Ed Taylor has done before. But here, in this case, one derive it. The special part is that you remember that this, because of the effective range, you have this square root of omega dependence in high frequency. So in that case, you have to subtract them out in order to obtain a finite sum rule. So that's slightly different from Ed's case, but Ed's case, in Ed Taylor's case, you have also to subtract out one term. If I remember, yeah, I think the divergent term. But here there is a more divergent term that you have to do. Yeah, so that's where the high frequency part, which I just discussed. But I think for for the experiments, I'm not so sure. But I think because you cannot change the scattering or effective range, in a way. So if one, let's say, if one in the Pwl case, if one just locate at resonance and just look at, for example, how the monopole mode damps, that will certainly, according to what we say, if it is correct, will give you a measure of the effective range in that, the contribution from the effective range.
Right. Yep.
Yeah, but I think in the S-wave case, I think they have done this experiment, right? So at resonance, the monopole damping is very, very small. So maybe that's relates to the fact in the S-wave case, in the kind of broad phase bar resonance, RE is anyway very, very small. So so maybe. But yeah, when you get into that very small quantities, you never know whether this one is the important one or any other effect is important. So
right.
Yeah.
Great. Okay, I'm going to stop the recording.
Okay. Good.